There's one final type of reaction that you'll need to know about um, for this particular chapter, and it's a very special type of reaction. It's actually a reaction we've looked at before, but we didn't call it what we're about to call it. So that's the redox reaction. So the redox reaction is short for oxidation reduction. And what an oxidation reduction reaction involves is the transfer of electrons or atoms between species. Okay, so a oxidation reduction reaction involves the transfer of electrons between reactants. Okay, so you're transferring specifically electrons between reactants. And so oxidation occurs when an atom or ion loses electrons, and reduction occurs when an atom or ion gains electrons. And so these electrons, these losses and gains of electrons, will always be characteristic of these redox reactions. So there's a couple of ways, a couple of mnemonic devices that you can use to remember which one oxidation is and which one reduction is. Oil rig is one of those mnemonic devices. An oil rig is basically just oxidation is loss of electrons, reduction is gain of electrons. The other one is Leo the lion goes grr. And I kind of like this one better because we get this nice Lion King picture. But for this one, Leo is loss of electrons, oxidation. Grr is gain of electrons, reduction. So Leo the lion goes grr, loss of electrons, oxidation, gain of electrons, reduction. So let's look at a couple of forms or a form for this and see how this works out with a balanced chemical equation, how you can identify this using a balanced chemical equation. So if you consider the equation below, what you have here is a neutral calcium going to a calcium 2 plus. Well, the only way that can happen is if this calcium atom loses 2 electrons. Well, if it's losing 2 electrons, it's got to be losing it to someplace. The other thing to look at is this hydrogen plus is going to form elemental hydrogen, and there are 2 of them here, right? So 2 hydrogen plus goes to form elemental hydrogen. Well, H plus has no electrons. This elemental hydrogen has 2 electrons in this molecule, right? It's a covalently bonded molecule, so each one of those hydrogens has to be contributing an electron. So you have a neutral atom as losing 2 electrons, become calcium 2 plus, and then that would be said to be oxidized. So the calcium is being oxidized in this particular case. And then you have a gain of electrons for the hydrogen. So hydrogen is gaining, the H plus is gaining 2 electrons, or each one is gaining an electron. And so it is being reduced. And notice that these things have to happen at the same time. Okay? So at the same time that this is being oxidized, this is being reduced. So there are a couple of things, just bookkeeping things that you need to do for redox reactions. One of them is, or the big thing is actually oxidation numbers, and this is kind of like the formal charges that we saw in a few chapters back where we were looking at Lewis structures. So oxidation numbers are kind of like formal charges, and they help us keep track of electrons, where electrons are going during these chemical reactions. One of the things that is important to remember is they are not necessarily real charges. Okay, they aren't actually charges on the different atoms or ions in the species. So keep that in mind. So we're looking at these. Here's some rules for assigning these oxidation numbers. The first rule is that an element in its elemental form, so for that, an element in its elemental form, the oxidation number is always 0. So if you look back at our original reaction, or the reaction we were using for an example, This calcium right here is in its elemental form, so its oxidation number would be 0. Second one, for any monatomic ion, the oxidation number equals the charge on the ion. That's also important, or dictates what this first example was, because if you look at this, these are monatomic ions. They have H plus, so their oxidation number is +1. Next rule, nonmetals usually have negative oxidation numbers, okay? So nonmetals usually have negative oxidation numbers, and specifically the oxidation number of oxygen is usually 2 minus. There's an exception to that in the peroxide ion. In the peroxide ion, the oxidation number for each oxygen is -1. So the next rule is that the oxidation number of hydrogen is +1 when bonded to a nonmetal and -1 when bonded to metals. Okay, so that's an important one. If you ever see hydrogen bonded to a nonmetal, it's going to be +1. If it's bonded to a metal, it's -1. The oxidation number of fluorine is -1 in all compounds. So every time you see a fluorine, it's -1. And most halogens, so other elements in the same group as fluorine, have an oxidation number of -1 in most binary compounds. Finally, the sum of the oxidation numbers of all atoms in a substance equals the overall charge. So in a neutral compound, the sum of all the oxidation numbers has to equal 0. In a polyatomic ion, the sum of the oxidation numbers equals the charge on that polyatomic. So this rule actually explains this rule, and this rule actually explains why the oxygens in peroxide are not -2. If you think about it, these hydrogens are bonded to this oxygen, which means these hydrogens are +1, right? So if this hydrogen is +1 and this one's +1, then each of these oxygens need to have a -1 charge in order to have an overall 0 for their sum of their oxidation numbers.